Greetings. Welcome back to our lecture series on Morse theory with no background. And today is our second part of our lecture on Morse functions and diffeomorphisms. So let's do a quick recap. So what did we cover last time? Last time we spent quite a few time going over this definition on Morse function, which is a very simple statement, right? So here I have it written on our notebook. As this is displayed on the board, we can see that a Morse function is that suppose that every critical point of the function f that's defined on some surface that maps to a real number r on this surface is degenerate. So every critical point on this surface is a non-degenerate critical point. Then we know that f is a Morse function. So a very simple statement, right? So we also gave an example in the last lecture. Basically, yeah, we have a sphere that looks like this, right? So let me draw a three-dimensional sphere, right? Here we go. And here we can see this will be the max and this will be the min if we are mapping the height of this um, sphere if we give this sphere a coordinate system, right? So x, y, and z, right? And let's assume that height is z. And basically, we have a function that's defined as f that maps from x and y to z, right? And z equals to plus or minus 1 minus x squared plus y squared. Great. And we also talked about double covering in the last lecture, which we'll discuss later too. And yeah, basically, why is this function not a Morse function? Basically, right, we can check if our critical points are all non-degenerate, right? So let me just make this red. Yeah. So every critical point needs to be non-degenerate, right? So first, for the time being, I'm just gonna tell you guys like the top and bottom will be the maximum and minimum, right? So like these 2 points, you can just do the derivative, right? So you take the derivative of this function in with respect to x and y, and then you find those 2 points, which I think corresponds to x equals to 0 and y equals to 0, right? And then we have 2 points, obviously, right? Because this maps to z equals to +1 and -1, right? So we have, yeah, x equals to 0 and y equals to 0, right? Coolio. And now we can basically find the Hessian on this point, correct? On these 2 points, right? So let me just skip some steps and tell you the first Hessian, let's just write h1 equals to -1, 0, 0, -1. And the second Hessian is 1, 0, 0, 1. And if we look at the eigenvalues here, right? So the two eigenvalues on the first one are both negative, which we just defined indexed in our previous lecture as well, right? So this means it has an index of 2 because um, it has a two negative signs in front of our eigenvalues, right? And same thing here, because we have no negative signs, both eigenvalues here slash the diagonal terms, because this is a diagonal matrix, we have an index of 0, right? Which these things can tell us the properties of our critical points, right? So basically, we know that this implies, oops, let me make this go down. Ooh. Um, so index 2 basically implies that we have a maximum here. And index 0 means we are at a minimum. Because our max dimension in our state is 2. So we already occupied all of our space with our index number. So if this just equals to state, then this is a maximum. And likewise, if we have an index of 0, then it has to be a minimum. And apparently I can't spell. Minimum. Minimum. Yep. Spelling is important, guys. All right. Let me erase this. And for some reason, I can't drag it down for some reason. Let's see. All right. I declare you to go down. Okay. There you go. Okay, great. Okay, so this should be pretty straightforward. Yeah, basically, this is a quick example of showing why this is a Morse function, and those 2 points are the only critical points that we have on our surface. So, yeah, we have these 2 points as well, non-degenerate points, critical points, namely maximum and minimum, and they are also global maximum and global minimum at the same time also local. And yeah, so this is a quick recap on what we've covered last time. So today, what are we going to cover? So as promised, we are going to cover diffeomorphism, my favorite topic to talk about, diffeomorphism. And to start with that, we're going to introduce a theorem, of course. And also, before we can talk about diffeomorphisms, maybe we also need to talk about something first. And this is sort of like a prereq for diffeomorphism. Maybe talk about this first. And this is called homeomorphism. I believe those two words both came from Greek. So like morphism is like morphing. So it's like changing, transforming from one to another, right? So diffeol, like this word, this prefix is kind of like differentiable diff. It's like difference, right? So it's kind of like taking a difference, taking a derivative, something like that. So it has something to do with like differentiability and homeo. And apparently I can't speak, I can't spell here. Wholemeal should be whole meal. Whoa, 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 whoa. That's pencil. My mistake. Yep. Whole meal morphism. And whole meal, well, what does whole meal mean? Whole meal, it kind of sounds like I don't know, maybe a homogeneity. Like homo kind of means human slash like the same, right? So like homeo actually means like something about continuous. Well, I think this is like somewhat related to the Greek language. I could be wrong, but I'm like 99% sure. Anyways, yeah, so this is what we're gonna cover today, and let's actually begin with a quick theorem that's super important. So let's write down our theorem statement. Theorem. So this is called diffeomorphic to S2. But recall what S2 is. S2 is the sphere, the surface of the sphere. Um, okay, so this is a theorem that we use diffeomorphism, which that's also why we're going to define diffeomorphism in a little bit. So what does this theorem say? The theorem says, let M be a closed surface. We kind of talk about what a closed surface is in a very non-rigorous way, which is going to be covered later too. And suppose that, recall this symbol. This means there exists. So suppose there exists a Morse function we denote as f that maps from the surface to some real number with exactly two non-degenerate critical points. Recall earlier the example that we just pointed out, the sphere itself had two non-degenerate critical points. And make sure that we have no other critical points. Then M is, okay, let's change color here. Diffeomorphic to the sphere S2. Okay, this is a very strong statement. Basically, if you're a topologist, assume you're not. If you are, then I guess like you're pretty much an expert in this area, and I think you'll appreciate this the most if you're a topologist. Basically, that means you can just like manipulate your space and then just like transform it, morph it, hence diffeomorphic, morph it into a sphere. So basically, your surface can be morphed into this sphere space, which is actually super, super cool. Because sphere is actually a very nice space to work with in terms of like a nonlinear space, of course. Because like, yeah, like sphere is a very, I guess, understood object of study. How about that? This is a object that we can picture, and it's easier for us to understand and easier to work with. And we'll see some examples about that later. And yeah, so I've been yapping about diffeomorphism for a while, and something is diffeomorphic to something. What really is diffeomorphism? So before we can talk about diffeomorphism, what it really is. So what is that? We need to talk about homeomorphism first, right? So I've been saying that homeomorphism is kind of like a prereq for this, right? So let's give it a quick definition. This is like one of the transformations that we need that is actually very nice. Because like especially for topologists too. Basically like I don't know if you heard of the joke that a coffee mug is basically a donut. They're indistinguishable. Basically for topologists, one thing that's homeomorphic to another, then those two things are topologically indistinguishable. So a single point and a disk, basically a bowl, they can be indistinguishable. But we'll talk about that later as well. So let's quickly give a definition on what diffeomorphism is. Definition. What is a homeomorphism? So let's define a function. H that maps from X to Y. Could be any space. That is one to one and onto. So what do those two words mean? So if you have taken analysis or any like higher level math course, you know that one-to-one means uh injective. Oops. And onto means surjective. So one-to-one basically it's like for every value in your domain, and then your domain maps to a single value in your target, in your range. Basically, that means one to one. If you have like a x squared, then it's not one to one, right? Because you have a one to two. Um, Actually, that was incorrect. What I just said, a sphere is actually a good example of that. Basically, for um, x squared, you still have one. Oh, yeah, right. So you don't have one to one. I was actually right. Sorry, I always confuse myself for some reason. Basically, one to one is that if you have this, right? Let me draw. Right. So you have one value, let's say 4, right? And there we have a 2 and we have a -2. So we don't have a unique value that we map to. So f of 2 maps to 4, and f of negative 2 also maps to 4. So that is not one-to-one anymore. Does that make sense? And onto basically means every range is being covered. So like the rigorous definitions, of course, is also out there. Those two are important definitions that you need to know when you learn analysis. And yeah, so quickly, I am not going to cover this in detail, but feel free to search those online. But yeah, those two are very important properties and on functions and on maps, right? So like this basically shows that what your function can cover, right? Like if the entire domain, uh, sorry, if the entire range is being covered, or like if you have a one-to-one relationship, something like that, right? And if you have both of those, this if you have injective plus surjective, then you will actually have something called bijective property. Yeah, bijective just means that you have both injection and surjection. So a function that is injective and surjective is bijective. Cool. And then now we also require our H inverse. So if we take the inverse of this function, which maps from y to x, this also will be bijective, right? This makes sense, right? So you map from one space to another, and then you map back. It is, yeah, it is. It still preserves these properties, injective and surjective, hence still bijective. And at the same time, these two functions, h and h inverse, are continuous. Then we have h is a homeomorphism. And we say that X and Y are homeomorphic if there is, oh, not this is, there is. If there is a homeomorphism. What does that mean? That means we if we have just one H, it can be non-unique, of course. There's multiple ways you can form this sort of mapping, right? So if you can find a map H that satisfy all this criteria and its inverse also satisfies this, and both of those, right, they're both continuous, then we know that those two spaces are homeomorphic, right? So, yeah, that's just the definition of that. And for topologists, yeah, that means those two spaces are indistinguishable. And now we can actually cover on what diffeomorphism is. So diffeomorphism is a little bit stronger than homeomorphism. It's also a very, very cool concept that's used in many areas of study. For example, one of my favorite field of study, control theory, which I'm a PhD student, by the way, in the Georgia Tech ECE department doing robotics, and a lot of my research are related to nonlinear controls and optimal controls. So in control theory, diffeomorphism is used a lot. And in robotics, something called near identity diffeomorphism is also introduced a lot, which, if I have time, maybe in the next lecture, I will introduce more stuff about more examples about these diffeomorphism implementations and the extension of I guess the raw the definition slash the very very abstract definition, I guess. But yeah, this is actually so widely used, and it's such a um, elegant, I would say, definition, and a very interesting definition. Because, like, also when I first learned about this word, I was like, wow, this is a big word. I've never heard of this word. I actually learned about this my second week in grad school, and my basically my boss told me, oh, this diffeomorphism is easy. So here, you just need this and that, the differentiability, and also you need bijective continuous map. And I was like, what is that supposed to mean? And then the more I learn about it, the more I was like, okay, okay, this makes sense. It's actually simple. It's just a big word. And let's stop yapping and start giving it a definition. So definition, diffeomorphism. So first, we've already defined what a homeomorphism is, right? So a homeomorphism, let's start with that, with something that we've already established. So this homeomorphism is a diffeomorphism if the maps H and H inverse, oops, are both of class C infinity. So recall what this is. This is smoothness, right? What does that entail? That means we can differentiate, right? So diffeomorphism literally just adds that differentiability on the two maps that we just defined, right? It makes sense because the name, it's in the name, right? Diffeomorphism, diffeol, right? So like it is supposed to be differentiable for the two maps. And then, yeah, so if we have these ingredients, then the two surfaces, M and N, are called diffeomorphic. If there is a diffeomorphism between them, right? So similar to homeomorphism, if there exists one, then we have a diffeomorphism, same thing as homeomorphism, right? So we just need one map whose inverse is right, it needs to be continuous, also needs to be bijective, and it needs to be smooth, right? So yeah, there we go. This is what diffeomorphism is. Right now, I don't know how you feel about this. It might be like overwhelming to you for, oh my gosh, this is kind of abstract, right? So you have so many ingredients. What for, right? Or it could be, oh, okay, this makes sense. I mean, it could be on anywhere on the spectrum. Well, what I'm trying to tell you is this is very important. I've said it a lot, and I think it's a very fun thing to talk about. But yeah, anyways, this is very, very right now it's just a definition, right? But this is very, very profound well, today I don't think we have enough time to cover all this, but I will give you guys more examples on different morphisms to try to convince you guys. It's actually a fun concept and it's very important. And a quick spoiler, real quick. So if you look at gradient descent, as some people you may know, gradient descent is a very important, or actually one of the greatest algorithms used in optimization. And most of machine learning algorithms, most machine learning models are actually trained with this algorithm, with maybe something called stochastic gradient descent. It's just a variation of it. But a gradient descent is actually a diffeomorphic map, a composition of it. If you learn more about it, you will find, oh my gosh, this is actually such an interesting concept. But right, I'm just talking about it, and maybe you don't have any intuition about it, which is fine. But this just really gets me excited about it because diffeomorphism is such an interesting concept. Yet, see, I'm talking about it again. But I will give you some concrete examples to prove to you. But here, we just listed a quick theorem in the very beginning, right? So, oh, where's the theorem? Yeah, here we go. There is the theorem to show that our M is diffeomorphic to the sphere, right? So we are going to try to prove the theorem using our definitions that we just covered, right? We covered the definitions for homeomorphism, right? And also diffeomorphism. And we're going to use these things to prove our theorem. So let's see if we have time for the entire proof. I think the proof is very, very involved again because I prepared this lecture a while ago, and this also took me quite a few pages. So let's actually maybe get started on the very beginning of the theorem, and we can call it for today. And let's do this. So proof. Let's give it a caveat. Caveat. I think that's how you spell caveat. It's very long. And this is also one of the most involved um, proofs that I really, really urge you to follow along. And I'm going to skip some mathematical detail. The more important thing, again, is for you to understand how this works and really appreciate the elegance of it, right? So, yeah, let's begin. So, first, we know that we have M is a closed surface, right? So, M being closed, in another way, we can say that M is compact. So compactness is a very also another very important concept in mathematics. In R, through Heim-Borel theorem, we know that it is bounded and closed. So, but let's not get into the detail of that. This is a very interesting and important analysis concept. And if you're interested, search up Heim-Borel. So I will Heim-Borel. I'll write this down for you to look at. And yeah, also you can just search up compactness. It will give you more information on that. Let's not get hung up on that. So basically, let's do a quick recap, not recap, but quick explanation. So we know that a closed surface is a two-dimensional compact manifold. Just take it as a fact because this is just also some mathematical jargon, right? All we want is some properties from these conditions, right? So yeah. And I'm pretty sure you guys don't want me to yap like 30 minutes about something that's like kind of trivial, right? Anyways, okay, so now we have compactness, right? And compactness plus continuity. So if something is compact and we have a continuous function, we can use, this is something very important. We can use the extreme value theorem. Again, this is a very important theorem in analysis. And again, analysis is very important. You should take a class in it if you are interested in this subject matter. And I think most mathematicians, well, all mathematicians should take it. Most engineers should take it because it's very important. And I think your brain will grow 3 sizes larger after taking the course. Anyways, yeah, so let's just do a quickly denote this, right? So we know that the function on this is Morse. Okay, okay, great. So what does extreme value theorem say? So in short, basically, if we have a compact set, the basically M is compact, right? And F is continuous. That means our maximum and minimum in our function are attained in our set. or I guess on M. Let's erase this. And let's write on here. Yeah, so our maximum and minimum are actually attained. So if you're familiar with supremum and infimum, so these are least upper bound and greatest lower bound. These things are not usually attained in your set because those are like bounds that kind of like are kind of like asymptotes, right? But if you have this compactness and continuity, then these supremum and infimum, these bounds are actually achieved and they can be replaced with maximum and minimum. So basically, in short, basically, you just have a max and min, and those values are in the set. Those values are achieved in your R, right? So you can evaluate these values when you take a value on your M. So like yeah, like your critical point actually maps to a value that corresponds to the min and max. That's what it is. Okay. So we can attain these, right? At some point. So let's say we attain, oops, this flew up. So at some point, P naught and Q naught on M, right? And they are both non-degenerate critical points, right? And let's say that P naught is maximum and Q naught is minimum, right? Just quickly, yeah, denote these points. I mean, you can interchange these, no problem. And by Morse lemma, we know that F can be put into a standard form, right? Because we have a Morse function and we can do this. So we can put some arbitrary coordinates neighborhood in this neighborhood around P naught and some arbitrary other coordinate, big X, big Y, about Q naught, right? So P naught will have an index of 2, and Q naught will have an index of 0, right? Because what is Q naught, right? Q naught is our min, and P naught is our max, which means this has like two negative values, right? For our Hessian. If we put it in a diagonalized form using our coordinate transform, right? And then for this, let's just write this H1 and H2. This will be like A and B, right? And let A is greater than 0 and B is greater than 0, right? Okay. Then we can basically kind of write the function in the form of this, right? So f will basically equals to small x squared minus small x squared minus y squared, small y squared, plus some a, right? A is a constant, the value at the point near p naught. And on the other hand, we have big X squared plus big Y squared plus some small a, which is the um, minimum, right? The value at the minimum near this critical point. So yeah, A and A are max and min respectively. Okay, so let's actually stop here because next we are going to do something kind of fun about looking at these neighborhoods and try to actually mm, I guess like look at the neighborhood around it and see what we can do with it, and really use the definition for a diffeomorphism slash the diffeomorphic relationship between two spaces. And yeah, and next lecture, we're also going to maybe chiming some examples, maybe at the end or in the beginning of the lecture, maybe probably at the end though. And hopefully we can prove this theorem, finish proving this theorem in the next lecture, which this will be the part three of this series on right, Morse functions and diffeomorphisms. And yeah, and again, diffeomorphisms are really fun concepts. And this lecture mostly consists of just, laying down the definition and then, this important theorem that we are trying to go over. And yeah, so next lecture we're gonna be keep doing that. And thank you guys for listening again. And I will see you guys next time.